Welcome, everybody. Let's get started. I'm Alex Hernandez. I'm happy to welcome everybody to our colloquium for the first day of March. And it was sunny earlier, it's not so sunny today. I'm pleasure to introduce Dr. Lorraine Lee, who's going to introduce.
Right, so yeah, today we are very fortunate to have friends from LTI and the usually for automating machine learning. So Frank's research focused on NLP, natural language processing, with a particular interest in fundamental applications, fundamentals applications, and understanding of large language. For tasks such as question answering, code generation, and multimodal applications. Its final goal is that everybody in the world should be able to communicate with each other in their own language. It also contributes to make NLP research more accessible to open publishing of research papers, advanced NLP courses, materials, and major lectures, and open critical topics, all of which are mobile. And I back a lot of that. So let's welcome our speaker today.
Hey everyone. So despite being in Pittsburgh for 7 years now, this is the first time I've ever come to CS or given a talk here. So I'm very happy to be able to come over and give a talk. This time I'll be talking about towards automating machine learning engineering. It's some work that me and some of the students in my lab have been working on. And so how many people here use machine learning in some way, like train a machine learning model or
Nobody.
probably most of people, I guess, nowadays. And so you're probably pretty familiar with the machine learning system development cycle. And basically, you start out with some sort of task that you want to be solving. And from this, you then might create training data, find a base model that you would want to be training, and train that model on your data to get a system. You have some testing data, you get an evaluation result, and from that evaluation result, you might get ideas and iteratively improve your systems until they get better and better. So this is something that I think a lot of people are familiar with, but it is also kind of limited to people who have some expertise in at the very least in computer science, probably in machine learning as well. And so my question that I want to ask here is, can we automate some steps of this cycle? And there has been a lot of research and work on automating a particular step of the cycle, and that is somehow optimizing the training process that we have. And this is often called like AutoML or automated machine learning. But what I want to talk about is something in different parts of the cycle, because all parts of the cycle are useful. And the first thing I want to talk about is, given a description of a task, how can we go out and find the best data sets and models to train our models on and go and train them to get better results? And another thing is, given an evaluation result, how can we very quickly get ideas to improve our methods? And I think both of these are, they might not replace the entire machine learning cycle, but they might make it easier for you or practitioners, people who are less skilled at machine learning build systems. And I'm going to talk about 3 different pieces of work that I've been working on. The first one is Datafinder, and this is scientific data set recommendation for natural language descriptions. And the basic motivation behind this work is that there's been a huge explosion in machine learning research in general. So if you're working on machine learning research, I'm sure you're very overwhelmed right now, like everybody else, with all the papers on archive, all the things that you need to keep up with. And the data sets are no exception, right? So this is a slightly out of date graph, so it's probably even worse in 2024. But this graph shows up until 2022, the number of data sets that are recorded in a data set repository called papers with code. And on the other hand, if we look at the data sets that people are actually using in machine learning, it's very peaky. So we have a few data sets that people are using a lot, and then most of the data sets that are expanding here, people aren't using very much. So it doesn't mean the other data sets aren't useful. It's just that they're hard to find, or you might not know the best data set for what would be. So that's a problem we tried to set out to solve here, to connect practitioners with the best data set. And the general idea is, we ask the question, can we build a system for data set recommendation that takes in natural language descriptions of a system that you want to build as input and spits out the best data sets and test or train that system? And there actually are existing tools for this. There's papers with Code Dataset Search and Google Dataset Search. These are things that exist. They have a database of data sets that you can search over. But they're actually surprisingly ineffective. And we measured a standard retrieval-based metric called mean average precision using these tools, where we either put in a longer natural language description of the data set we wanted with lots of details, or just picked out keywords. And neither of them were particularly effective. We hoped that would do a lot better. So basically what we did, this is kind of fundamental work towards the bigger vision, but we created a data set for this task and a strong baseline system that allowed, you to go in and search for new data sets. And so the way we did this is we wanted to create a system that both is able to take natural language queries where you write, like, I want to use adversarial learning to perform domain adaptation for semantic segmentation of images. It's like a description of the task you want to do or the research project that you want to do. And it would allow you to go and find a data set or keyword queries like semantic segmentation, domain adaptation to the text. Because we're all familiar with these sorts of queries. We also came up with some implicit constraints. So we annotated the data set with metadata. So like semantic segmentation is the task, but modality is images, and other constraints are like the data set should include diverse domains. And we collected a fair amount of data from human annotators, aka CMU graduate students. And they basically went in and looked at papers and said, okay, what is the task? What is the modality? What are the other constraints that we might look at? So this is kind of an evaluation data set for data set search. So if your task is, I want to perform data set search, this is the data set that our Datafinder should return to you. So Datafinder model, the Datafinder model we created, it's actually relatively simple. It's not super complex architecture-wise, but it's a neural bioencoder model. It's based on a pre-trained model called Cyber, which we chose because this is a version of BERT that was trained on scientific articles, so it would be better for, we assumed it would be better for this kind of task. And we trained it using some standard best practices for retrieval-based model training. For example, we selected hard negatives to train the model using kind of keyword-based search, so it would be able to discriminate between like very similar things and not similar things. And the queries include both the data set description and the structured metadata. So we can turn those into any format that we want to train them on. We did lots of ablations on the base model and other stuff like that. This is all in the paper. And basically, what we found is Datafinder beats the third-party dataset search engines, both on keyword and natural language search. So this might be a good tool that you could use next time you have a project that you would want to do and say, like, try to find data sets that you might see. There's still a lot of room for improvement. So if you're interested in, for example, machine learning or natural language processing for improving scientific, improving science, this is a data set that you could, build a system for and improve. So I think that could be, that might be interesting in some subset of. But this is really just warm up for our bigger vision of some stuff that we're doing here. I should point out that this is available online and you can use it, but it's available as part of our second system that I'm going to talk about. So I'll point out how you use Datafinder after I talk about this. But are there any questions about the Datafinder?
Well, so did you? I probably missed that. Did you create the data set? Was that just for verification of the existing data that you have? Or for this to work going forward, you need this CMU studies to keep annotating the new data sets as they become available?
Yeah, so this this is for verification, for, actually, I think I'm sorry, I forgot to mention this on the slide, but we created testing data manually, and we created training data semi-automatically by basically extracting it from paper abstracts. I thought I had a slide about that, but maybe I didn't.
You may have said it,
No, I didn't say it, no, but yeah, we created training data semi-automatically by using paper abstracts and identified which data sets were used. Yeah.
So one thing that's different with this implementation is that it, in the case of Google or paper source code, you actually have the search field and you can type the values and you get the output, right?
Yeah.
You get the. But I just opened a report. It's like you have to run this script and then it gives it as output in the shell, or like does it download the data set or?
Yeah, so, our implementation is part of, this prompt model system is, you can actually run it through a Colab notebook, so it's a little bit easier, and then you can go in and download the actual things. Anyway, maybe I'll go into the second part, because this is kind of the bigger vision, that we have, for more complete automation of the machine learning pipeline. And so, the title of the paper is Prompt Model, Generating Deployable Models from Natural Language Instructions. And the basic idea here is, I talked about this machine learning training pipeline that a lot of people are doing if they're building a machine learning model. There might be some people who are like, oh, but wait, I'm building machine learning systems, but I'm not doing this because now there's a new way that you can create machine learning systems, which is prompting large language models. So you have something like ChatGPT or something like this, which is just kind of a general purpose large language model where you put in your task description, where your task description could be, just to give an example, I would like to translate a Japanese command into a Python program or something like that. And then you have maybe a few examples of what that looks like. You might have, a Japanese sentence and then a Python program for that, and then you just feed that into ChatGPT or something, and it does it for you. And so this is very new. Like we wrote a survey paper about this in 2021, when it was just getting started, and it's been 3 years, but now it's almost the dominant paradigm for how people are building natural language processing systems. And so that is great, but there's also a lot of problems with this. And the problems with this are manifold. Number one, lack of privacy. So many people want to run things locally and get models to work without sending their private data to a big company that's processing it in some way that you're not sure about. Another thing is cost. So using large models is expensive. It's not just expensive for us, it's also expensive for the people who are serving large models. And so ideally, you might want to use a smaller model, even if it is being served by somebody else. The problem is small models don't work really well on all of the tasks we want them to do. The other thing is control. So like, let's say you want really fine-grained control about how the model behaves. It's not super easy to do that from just prompting large language models. And you really kind of training a model yourself is a better way to get very fine-grained control about the way things work or fix, particular error cases that you really don't. So the idea here was we want to kind of take the best of both worlds. We want a method for solving the task of going from a task description. So in other words, the input to prompt model is exactly the same as the input to ChatGPT. It's just the task description, maybe a few examples. And the output is a small trained language model that can be locally deployed and you own yourself. You can use it in any way you want. And so that solves the problem of privacy because you can deploy it yourself, cost because it's small and easy to run, and control because then once you get this model, you can modify it in any way you want. So it combines the ease of something like an OpenAI GPT and the privacy cost. So basically, what we did is we said, okay, what are machine learning engineers doing, or what are smart University of Pittsburgh, graduate or undergraduate researchers doing. And basically, the workflow is we get training data, we get a base model, and we train the system. And so how can we do that automatically? So we came up with some methods to do data set retrieval and generation or curation. Model retrieval, so trying to find the best model that we could use in a particular thing, and also training. So the way that data set retrieval works, I've kind of already told you what we do here. We search against the Hugging Face datasets repository, which is a big repository for many, pre-trained models that people can use. And we search against Hugging Face datasets using something called a dataset card. And the dataset card is basically a description of the dataset in English about what the dataset is. And we more or less use Datafinder as is. And so this, I've already told you how we do this. However, one problem is there aren't necessarily datasets in the Hugging Face repository for everything we want to be doing. So, for example, I gave the example of Japanese to Python generation, and there is no data set for training Japanese to Python models in Hugging Face. There's a data set for evaluating Japanese to Python models, so we can, for the purpose of this paper, we evaluated, but there's, many other tasks where datasets don't, exist. So because of that, we also added generation component that allows us to generate synthetic data. And so to support all tasks, we additionally generated labeled data using a large language model. And here we can use a large language model to generate data because in the end, we're not going to be using this large language model in our actual system. We're just using it in training time. Specifically, we use GPT 3.5 Turbo because it's cheaper than GPT 4, but we could use something else. So this was our basic idea, but when doing this, we ran into a bunch of challenges about how to get models to generate data in a way that was actually useful. So some of them are, they all boil down to how to generate diverse yet high quality data automatically. It's very easy to get diverse data. It's very easy to get high quality data, but it's hard to get diverse and high quality data. And so basically what we did was we first used methods that allowed us to get high quality synthetic data. And the way we did this is we fed in the task description and a few examples. For each of our tasks, we provided 3 examples total, because we figure that if you really care about a task, you can create a small number of examples about how the task works. And we basically asked a language model to generate similar examples to the ones we already provided. But we had it generate at a low temperature. And basically what a low temperature means is we want the model to sample outputs, but we want it to sample outputs that have high probability. And the output, like empirically, we saw that the outputs that we sampled with high probability were high quality. They were not diverse, however. We would get very similar things because we were only generating high probability. So after that, what we did is instead of taking the examples, they don't go away here, right? Instead of is there one? Okay, great.
At least one of us is prepared.
Okay, thank you. Several.
I don't know if that one. Okay, that one.
No, take both because I'm not sure.
Yeah, so basically we start with like 3 examples. And these are all manually created. We generate more examples using a low temperature, like a temperature of 0.4. So this gives us like some high quality examples that are not very diverse. And then we add these and feed these into the large language model and say, generate examples like these. But now we have like 100 high quality examples, so we can randomize them and feed them into the model. And then we generate with a slightly higher number, like 0.6 or 0.8, 1.1 and stuff. So that allows us to kind of branch out and get more.
What are you doing if I high quality? How do I decide?
Yeah, so high quality means 2 things. Usually an example is an input X and an output Y. And so this means that X has to be kind of natural sounding. It has, like, for example, for the Japanese Typon example, it has to be like natural sounding Japanese. And then for the output has to be both natural and associated with it. So it has to be correct. So for a classification task, the like label would have to be correct. So it's both of those two things.
I have two questions. One, are all of these data sets generated natural language data?
Right now, yes. So I have some future ideas for work based on this later, and multimodality is one of them, but right now it's all language or code.
Yeah, so for two, I was wondering if you have plans to add like domain experts constraints in domains that are not really explored, such as like tabular data, for example.
Yeah, tabular data is a really interesting one because like tabular data is so diverse, right? There's so many, tabular data literally represent anything. Because it's just feature vectors over some sort of data that you care about. So we weren't thinking about tabular data at the moment. We were thinking about things like images and video or speech or things like that. How to do tabular data would be a cool challenge. There are some like general purpose tabular data learning methods, but I'm not super familiar.
I'm thinking this would be like very efficient for domains like financial domain, any other domain that do not have any.
Yeah, I think it really depends on whether you have a good generative model of the data. I also actually have some, I can talk some more about some future things for things about it.
It's hard to use over general.
Over generating and filtering, we did not try that, but it seems cool. The next thing is, oh yeah, sure.
You go back to the right. Okay, yeah. So you said your first generated example was lower 10%, then added those examples when you increase 10%, right? But then what's the advantage of that approach instead of just keep increasing it 10% without adding any example from low 10%?
Yeah. So I think the advantage of this is basically like if you keep on using these ones as the seed examples, it's just going to limit your diversity a lot because like even humans have a lack of diversity, right? And especially if you're only generating examples. If you could get these like naturally and get a whole bunch of natural ones, there would be definitely be better. And yeah, one of our future works, I'll talk about that. It's not in the slides, but we're just about to release it. How do we guarantee correctness? We don't guarantee correctness. We just try our best. Which is the same for all synthetic data generation. Cool. So next I'll go to model retrieval. Thank you for all the questions, by the way. They're great questions. So model retrieval, to do this, we search against Hugging Face models using their model card. Model cards are like dataset cards, so they explain what the model does. This is a lot harder than dataset search for two reasons. The first reason is it's really clear that a dataset is for a specific task. It's not very clear that a model is for a specific task. And in fact, there are certain kind of more general purpose models that are actually really good at a bunch of tasks. And so doing this search is difficult. The other reason is people like don't write model cards as well as they write dataset cards for some reason. Like people who make datasets like writing about them, people who make models like running lots of experiments and making the GPUs still work. So it's kind of like the descriptions, natural language descriptions people write are not good. So in order to do this, we tried a few things. The first thing we tried is using something called hypothetical document embeddings. And what hypothetical document embeddings are is we take something like your task is to generate an answer to a natural question. In this task, the input is a string that consists of both the question and the context passage. And we tell the large language model please generate a model card for a model that solves this task. And then the large language model generates this document. And we try to find other model cards that look similar to this. And this was originally created for search. It's a method called hide for hypothetical document embeddings. But we tried using this here. Nonetheless, this doesn't work super well. And so we additionally relied on both this and scaling by the number of times the model was downloaded. And so basically, this allows us to retrieve models that are both popular and a good match. In the end, this will largely resulted in us downloading really popular models, which is good because the really popular models are good models for a lot of tasks. So I think there's a lot of room for improvement for how we could make this work better. Once we retrieve a model in a data set, we just fine tune the model. So we convert all data sets into a text-to-text format. And we only considered text-to-text models as the previous question. And we considered only autoregressive language models. So language models that either are like an encoder-decoder model or just a decoder-only model, which is, if you're familiar with NLP, it's models like GPT-2, Llama, other things like that, for a decoder-only model, or T5 for encoder-decoder models. So we limited these types of models. We shuffled the generated and retrieved data sets together and fine-tuned with the default type. So that's what we did. Finally, one other really interesting thing after the development of prompting models for like ChatGPT or other things like that is it's actually harder to evaluate an NLP system than it is to build one. Because in order to build an NLP system, you are certain varieties of NLP systems. Let me say systems that are taken, an input and generated an output. You just need to send a prompt to a GPT model and it will do something for you, right? But you have no idea whether it's working or not because you don't have any evaluation data. So in order to fix this problem, we also automatically generated evaluation data and evaluated against our automatically generated data. And the way we did this is we basically just held out some data from the retrieved and generated data sets and evaluated against them. This may sound like a horrible idea because we're evaluating our system against automatically generated data, but it actually will show it's not so horrible. It's only a little. So here are experiments. In the original prompt to model paper, we experimented on 3 tasks. We wanted to cover the broad spectrum of the different types of tasks that people might want to handle with this. And so first we evaluated on a very standard task. This is a task called SWOT, or machine reading question answering, where you're answering questions about Wikipedia articles. For this, we have data and models are available. For the second one, this is the running example I had of Japanese to Python code generation. Here, some data is available, but not data right in the task that we want. There's data for like English to Python code generation, but not Japanese to Python. And then another one is temporal expression normalization. And basically what this is doing is saying, I want to get lunch tomorrow at 1 p.m. And then this needs to normalize that into 2024-03-02 in the space 13:00 or something. So this gives you this is a kind of niche task that there's no data sets on Hugging Face that handle this, but it's still something that a ChatGPT style model can do. So here are our results. First, on the bottom, we have GPT 3.5 Turbo. So this is, if you just use the large language model that we use as a teacher out of the box. And then on the top, we have prompt to model. And so prompt to model, basically, we can see that using both the retrieved models and retrieved data and generated data, we can actually do better than GPT 3.5 Turbo on 2 out of 3 of these tasks. The Japanese to Python task we were not able to do as well on. And the main reason why is there were no models in the size of model class that we were considering that really were really good at Japanese and Python at that time. There might be better models now, but when we did this experiment, these experiments, they were not. So yeah, let's see.
So, actually, I wanted how to actually accommodate for mechanical inside GPT 3.5 itself, because my basic cloud is already used in featuring.
Yeah, it's true. So just to repeat the question is how do we account for the fact that like data might be leaking into the large language models? We try to evaluate on kind of less common tasks for precisely this reason to avoid, data leakage, but really, this is kind of a general problem with using benchmarks that have been around for a long time. It's a lot of got leaked into the data. We didn't do anything really special. So yeah, and this is a problem. We're working better on supporting multilingual text and also just having better base models will help out with this as well. There's a few. So yeah, then what about evaluation? So all of the things that I showed in this previous slide are evaluation on real data sets that were created by humans. But what happens if we automatically evaluate on automatically created data sets? And what we're showing here is on the x-axis, this is the accuracy on the real test set. On the y-axis, this is the accuracy on the generated test set of various like choices of our model and various iterations of our model. And what we can see is that in some cases, or in overall, there is a reasonably good correlation between models, especially if you consider models that are really bad and really good. And we can see that the automatically generated test sets approximate reasonably well. However, the problem is up here. So what you can see is for all of the really bad models, there's actually a really strong correlation. Like if we consider all the models, there's a really strong correlation between automatic evaluation and manually created evaluation. But if you get to the really best models, there's actually an anti-correlation between the automatic evaluation and the manually generated evaluation. So what we can say is automatically generated data sets are okay at telling the difference between models that are really bad and really good, but they might not be great for data, like model selection between models that are really good. And so we might need a better, better methods for automatic test set creation.
Yeah. What can you use to say if a model is good or bad at generating?
So we use the evaluation metrics that we're using depend on the task that we're solving. For something like question answering, there's two standard metrics. I think we're using exact match here. So it's just whether you get exactly the answer that's annotated in the data set. So you need a data set that has, inputs and annotated answers. Temporal expression and Python code generation, we're using something called CareApp. And basically what this is doing is this is looking at the overlap between short text strings between the input and the output, and specifically character strings up to like 6 characters long, and checking the F measure between, which is like how often you get the correct strings that are in the output and how often are that strings that you output. We also compared price between using certain amounts of training data. So if we do retrieval only, this means that we just find the best data set and retrieve data from the best data set in case and we train the model. This is basically free because our retrieval model is very cheap to run. Generation with GPT 3.5 cost about $5 to generate 3,000 examples. So it costs about $5. And then according to the squad paper, it costs about $540 to generate 3,000 examples. So we can see that basically it's much cheaper and faster to generate data using the model. And using. Actually, I think this is wrong. I think this is retrieval and generation. So if we did retrieval and generation, we see we get 61.5 accuracy, which is similar to creating half the data by. So it's more viable solution. Cool. And so one thing I should point out is for this, we made a particular effort to make this number one modular and number two easy to, easy to incorporate in other things that you want to use. So if you go to the prompt model repository, we have a Colloquium notebook that you can run through and generate examples. Each component of this can also be ripped out and used separately. So like, let's say you only want to use the dataset search to find datasets, for the model search to find models or something like that, you can do that too. So if this sounds interesting, I encourage you to go in and play around with it and complain about it on the GitHub. And I can take questions, but I'd like to talk a little bit about the future challenges. I made these slides about a few months ago, so actually we're already working on or nearly finished with a few of these. One is better benchmarking on many tasks. So we only evaluated on 3 tasks here. Now we have started doing benchmarking on a bigger benchmark called Big Bench that has lots of different tasks. So we're expanding, but I would like to expand even further, especially to like multimodal data sets or like image or any other variety of data. Better data set and model retrievers. So one problem with data set and model retrieval is it's relying very heavily on the dataset cards that humans created, and very often these are not very good. So right now we're working on something where we actually look at the content of the dataset and look up data examples that are similar in content to the example, like the 3 examples that we provided. And this seems to be bearing some good fruit. What we haven't started working on this yet, but I think it's a really promising future direction, because right now we have a big pipeline system where each component is kind of optimized individually, but in the end, we really care about our accuracy at the end of the whole process. So how could we kind of optimize the whole process to create the best system here? And that's something we haven't even started yet. Another interesting thing is better learning under compute constraints. So we could theoretically explore the space of models to train for, 100,000 GPU hours, and we would probably get a marginally better model. But what we really want is we want a model that is we can get very quickly, it's very accessible to train. So how can we come up with like a good theory of like identifying which models are cheap to run, or which training processes are cheap to run? How can we optimize given, a certain number of GPU hours to yeah, and finally multimodal. So yeah, that's the overview of the prompt model part that we have today.
Yeah, so in prompt model, we sure you are controlling the diversity of the sample through the generation process. But say if like you wanted to retrieve a data set which is diverse, or say you wanted to like find the retrieve data sets by diversity by quality, how would you go about?
Yeah, so like if we wanted to take a look at the retrieved data sets by diversity or quality, it's a little bit tough because you need to have a notion of what diversity or quality means. Usually for the retrieved data sets, we're kind of assuming that they're high quality because they were created by humans, but that's not necessarily right. So if you can use humans in the loop to do that, you can always have humans verify, but if you want to do it automatically, there are a few methods to do this. Just to pick out one, it's not my own work, but it's nice work. So there's this paper, and basically what they do is they have some concept of the easy to learn and hard to learn examples. And the way they do this is they look at how much the probability of a particular answer varies, based on like training epochs. And the ones that vary a lot are ones that are likely to be noisy. So there certainly are methods that you can use to do that sort of thing, but it's not something we've examined in this context.
Yeah, I'd imagine something like that would be pretty expensive.
Well, if you're doing multiple epochs over the data, you get this for free basically, because you just need to record like the probability of each example in each training step. But yeah, there's probably lots of other things you can do too. But
I guess, yeah, you could do ones for each set and have that.
yeah,
We have plans to also generate the code and deploying further well, like for people who are not really computer science majors. Or like will not have the code, we plan to add a pipeline to also generate the code and train it automatically.
so if I were making a startup company, I would do that. I'm not. Right now, my upper bound of accessibility is a Colloquium notebook. But I think that would be, great if somebody did that, basically. So I could see a thing where it's like literally you put in your prompt and the prompt that you want to run with few examples, and then it generates a model for you to place it on the cloud or something like that. So,
Can you comment on the size of the data sets that you generate and the balance?
yeah, so the size of the data sets, I think for class, if I remember correctly, we've had different settings for different experiments, but I think in the paper we generated 3,000 examples, so it's not very many. When you say balance, what do you mean by balance?
Some data sets are balanced, they're imbalanced based on.
Oh, yes. Data set, if we're talking purely about classification, if we're talking about classification tests, there's, label balance, where it's like you want positive things and negative things. Language models are pretty bad at doing that. They're pretty bad at generating balanced data sets. So if you have an idea about what all your labels are, if you want balanced labels, you can force the model to do that by basically saying generate a positive example and I'll generate a negative example. And we found that pretty important. None of the things we did here are classification tasks. They're all generation tasks. So we didn't worry about that quite as much, but our more recent research, we are doing classification. Separately from that, there's a question of whether this will actually cover the things that users ask you to do. So maybe like the temporal expression normalization, it only talks about 2021 because that's the knowledge cutoff of GPT 3.5 or something like that. And so that would be bad, I guess. And so I think that's just kind of inherently a problem. One way we're looking to fix it now is we're looking to take we're taking retrieved data sets and generating based on the retrieved data sets. It's kind of a natural extension of what we did here, but there were a few nuances to get it right, and we're going to have a think about that. That improves diversity of thought. Cool. Yeah.
I don't mean that next would be this question like this. So you mentioned you get Python information test. There are English Python information tests. But is it possible to take it on, for example, your reference to English and
yeah, it's totally possible to compose models and say like we're going to do Japanese English and then English. The problem with that is if any one of them fails, you get pipeline errors. But there's basically two ways, like multilingual stuff is just one example of this, obviously, but for multilingual stuff, there's two common ways that people do this. The first way that they do this is they compose models. So they essentially have like a translation model, and then they have a code generation model. Another way they do it is they translate the training data. So you have English Python training data, and then you translate the English to Japanese and train a signal. And these are called like translate test, translate train. So our method of converting retrieved data sets that I just mentioned, that we're working on releasing a paper about soon, does the translate train style approach, but not just for across languages, also across, like if you have a data set that's a little bit different than what we actually want. I love this problem because it's like, if we solve this problem, we solve so many things in machine learning in general. So, but like, obviously, we're not going to solve machine learning overnight. So there's like a lot of things that we need to do in order to make this happen. Cool. Okay. So the final thing I'd like to talk about is going to be in a completely different variety. It's how do we, and this is a software project called Zeno, but also just kind of more generally about automatic error analysis in natural, not just natural language processing, but machine learning in general. So another important part of the process, especially if we're not doing something completely automated, but we're doing it by hand, is if we get an evaluation result from a test data set, we want to get ideas that allow us to improve our models. But how do we do this? And I think how well you can do this, or how quickly you can do this, actually improves your efficiency a lot as a machine learning practitioner or engineer or researcher. So our idea is to come up with methods that make this easier. And AI evaluation today, basically, there's a bunch of different ways that people do this. You could have big benchmarks that require lots of human created data. Or what a lot of people do is like developers just spot check and look at individual failures that people are working on. You can get end user feedback and other things like this. And also recently people have actually been using large language models to evaluate the outputs. But none of these specifically, so there's a bunch of different problems with these. Benchmarks can be unrepresentative. Human feedback is slow and not scalable. As I already said in my previous slide, LLMs might give you feedback that's not perfect, and it might have errors. And both of these are expensive and slow. So our idea is, or what we normally do is we have an evaluation set, and from this evaluation set, we get a number like 51% accuracy. And this is great for comparing systems on average accuracy, but it doesn't really give you an idea of what to do next. And so if we have our 21.3 average word error rate on something like audio transcription, what we would like to know is things like, does my model work for non-English languages? Does my model correctly add punctuation? Does it work with lots of background noise? Other things like this. And if we realize that the answer to any one of these is like false, it's actually pretty clear how we fix the model. We either add more data, or we take the data that we already have of that variety, and we modify it, or like if it's not correctly adding punctuation, we make sure punctuation is in our training data. So singular aggregate metrics aren't a sufficient representation of model performance. And so from about 10 years ago, one of the things I've done very broadly is instead of just looking at metrics, sample 100 or 200 examples, go through all of them and try to note all of the failures that the model is encountering, try to find the most common one and go in and fix it. And this has been very valuable for me. I first started doing this when I was an intern at Google because they made me do this. And I was like, I don't want to do this. But then I'm really glad that they made me do it. But then because this is very efficient, I've been working since then to create interfaces to make that easier. And I started out with a simple interface that did some analysis and wrote out an HTML file. But then I realized that human-computer interaction students know how to make beautiful and really easy to use interfaces. So this is my most recent, attempt at this, and it's an interface called Zeno. And it allows you to do data exploration, model comparison, and interactive reports. And it's much easier to actually look at how it works and need to demo it rather than about it, but, this is an example of an analysis of a translation system. And this translation system is translating from lots of different, from English into lots of different languages. And so on the right side, you can look at your data. And this is not particularly informative for most of the people in this room because most of us don't speak the languages on the right. So this is a particularly hard example of analyzing and understanding the model. But you can do some interesting things. So like one of the first things that you would like to do is say, oh, how well is my model doing on particular languages? So you can go to this, plot here and look at, okay, these are all the languages, and I can see that GPT-4, which is a very strong model, is doing quite well. It's doing better than this open source model NLLB on many languages like Romanian, but the worst languages are doing worse for GPT-4. So GPT-4 is not super great at translating hard to translate things. So this is one thing you can see. Another interesting thing that you can do, so you can make all kinds of charts. That's kind of something that you could do with Matplotlib or any other Python tool if you wanted to, but this just makes it faster. Another interesting thing you can do is say, oh, I want to look at all of the examples where the score is low. So what's wrong? Show me all the examples where the score is low. And so you select the place where this RF score is low. And immediately you're starting to see things like, oh, why is GPT-4 repeating things all the time? Here it's dropping, compared to the output, it's dropping lots of things. Yeah, it's dropping lots of content here to not generate the output. So that's another thing you can do. Another thing is putting two models side by side. So let's put GPT-4 next to the open source model and find the example where the difference between the two models is the highest. And I'll find models where GPT-4 is doing much worse than the open source model. Yeah, it's repeating all the time. It's dropping content. GPT-4, like obviously it's hard to modify because it's not an open source model, so we can't go in and make any improvements to it. But if we look at the open source model and say, oh, I want to look at the places where the open source model underperforms GPT-4. Normally this is a lot easier. Normally it shows you some examples where it's like in the wrong language, where the output's in the wrong language. And so it's like, oh, I want to go and make sure that my model is up. So the other thing that you can do is like come up with slices. So I want to identify slices where the model repeats itself multiple times. So here are examples where GPT-4 here are examples where GPT-4 repeats the same word multiple times. So we have like, you can see that it's happening lots of things, and we can look at, oh, it's repeating itself multiple times in many different ways. So basically, the idea is this gives you a way to very quickly explore data and better understand the types of problems that you're having here and improve the results. And this interface is really nice. I like it a lot. I use it a lot. Basically, what you do is you turn all of your data into like a pandas data frame, which I think a lot of people use, and upload it, and it gives you a browsing interface like this. But there's basically, I feel, 2 to 3 different important things that you need to be able to do, regardless of whether you're using Zeno or not. The first thing is slicing data. So you find subsets of data where your model is not working well, and there's some you can do that either manually by like looking for, oh, I want to look for things with particular metadata values, such as language. So I want to look at, you know, Mesopotamian Arabic, or I want to look at Irish, or something like this. Or you can automatically discover places where your model is under. And there's methods that allow you to do this, like some of the names are domino or slice method or things like that. So I think basically what I want to say in this part of the talk is if you are doing any sort of machine learning engineering, taking advantage of the most recent interfaces or automatic methods to do this sort of like evaluation to idea pipeline is a really useful. So yeah, that's basically what I wanted to talk about today. And I see we're at 59 past. So I spent most of my time with the first part and didn't get to talk a lot about the second part, but I have to talk more about that. Yeah, thank you.
What are some comparisons with one DB.ai?
So weights and biases is a thing that a lot of people use. It's mostly used for experimental tracking, so it's tracking your like loss curves and other stuff like that. It does have some methods for like visualizing data and stuff. The main thing here is this is attempting to slice data in interesting ways to try to find places where your model's underperforming, or view data side by side and do the like sorting and the relative comparisons. But the basic idea is this is designed to make it as easy as possible to go from like your evaluation results to identifying systematic failures. That's not something that we do.
And these are like static data, right? Like it's already these are already generated model outputs and
Yeah.
stored
Yeah,
in
they
a
are.
server like that.
There's other things that you can do, like you can do like adversarial attacks against the model where you try to generate things that are particularly difficult for the model to do, but that's not. Okay, thank you, everyone. I'm happy to